Let us solve some problems related to eigenvalues and eigenvectors. So we are given a transformation matrix A equal to 1, 2, 3, 2. Now we have to find the special vectors whose direction remains unchanged under the transformation represented by A and find the corresponding scaling factors. So we have already seen how to solve such type of problems. A minus lambda I times x equal to 0. Let's substitute. We get matrix 1, 2, 3, 2 minus lambda 0, 0 lambda equal to 0. We take the determinant 1 minus lambda, 2 minus 0, 2, 3 minus 0, 3, 2 minus lambda equal to 0. See, all these steps we have already discussed it in the previous session. Now, evaluate the determinant. 1 minus lambda times 2 minus lambda minus 3 times 2, 6 equal to 0. Simplified, we get lambda square minus 3 lambda minus 4 equal to 0, which is a quadratic or more generally a polynomial called the characteristic polynomial. Now we solve for lambda. We get lambda equal to 4 and lambda equal to minus 1. So these are the eigenvalues. Now for these eigenvalues, we have to find the eigenvectors. So let's take lambda equal to 4. Substituting it, we get 1 minus 4, 2, 3, 2 minus 4 times x1, x2 equal to 0. Simplifying it, we get minus 3, 2, 3 minus 2 times x1, x2 equal to 0, 0. Now we reduce the transformation matrix. R2 replaced with R2 plus R1, which gives us 3 plus minus 3, which is 0, minus 2 plus 2, 0. So we have reduced the matrix, which is the transformation matrix. Now here you notice that the rank of this matrix is 1. Number of variables, that is the components of the vector, is 2. So that means there is one free variable. So let's convert this into the equation form. We get minus 3x1 plus 2x2 equal to 0. 3x1 equal to 2x2. x1 is equal to 2x2 by 3. So here x2 is the free variable. So let x2 equal to k. Then we get x1 equal to 2k by 3 and x2 equal to k. So in this case, the general form of eigenvector would be 2k by 3 and k. One of the vectors would be for k equal to 1, which gives us vector v1 equal to 2 by 3, 1. Another vector could be k equal to 3. We just take values of k, different values of k to arrive at different vectors. So v2 vector equal to 2, 3. So here, this is vector 2, 2, 3. This is v1 purple. Another vector we could take k equal to minus 2. So v3 equal to minus 4 by 3 minus 2. So here the direction gets reversed, but it lies on the same line. So that was in case of the eigenvalue lambda equal to 4. Now let's take the other case, lambda equal to minus 1. So when lambda is equal to minus 1, we get the transformer as 1 minus minus 1, 2, 3, 2 minus minus 1. Simplifying it, we get this. And now reducing the transformer, we get 2, 2, 0, 0. So here again, rank is 1. Number of variables is 2. So 2 minus 1, 1. So there is one free variable. So convert this into equation from 2x1 plus 2x2 equal to 0, 2x1 equal to minus 2x2, x1 equal to minus x2. So that x2 is our free variable. So let x2 equal to k. Then x1 equal to minus k and x2 equal to k. So in this case, the eigenvector would be u equal to minus k, k. Now let's put some values of k. So k equal to 1 gives us minus 1, 1. This is the vector u1. K equal to minus 2 gives us 2, minus 2. This is our vector. For k equal to 3, we get minus 3, 3. So that is this vector. So we have found the eigenvalues and we have found the eigenvectors. Notice that varying k gives solutions on a straight line passing through the origin. Each eigenvalue has its own eigenspace, the straight lines passing through the origin. So let me bring in the vectors related to the other eigenvalue. So we have one line here, one line here. So if we take the infinite straight lines generated by these vectors are the solution space corresponding to the eigenvalues and forms a one-dimensional subspace called the eigenspace. So for lambda equal to 4, this straight line, infinite straight line would be the eigenspace. And for lambda equal to minus 1, this would be the eigenspace. And the way we would write it is eigenspace for lambda equal to 4 is equal to the span of the multiple of this vector. Similarly, eigenspace of lambda equal to minus 1, 1 is equal to span of this vector, where remember k is in real numbers. That was one example of eigenvalues and eigenvectors problems. In the next session, we will look at another. That's it for now.